Once we have a discrete probability distribution, there are several things we can do with it. We can find the mean and the standard deviation. The mean is the middle of the data set, and what in this case it looks at is what we would expect, and that's the keyword expect, to happen over the long term. Over the long term, things would happen differently than any one given experiment. So what we have here is we have 3 jelly beans, and I have the possible things that could happen. They all could be purple, or none of them could be purple, and everything in between. In my group, I could have 0, 1, 2, or 3 purple jelly beans, and the probability is given here. And you can see this bag must contain a lot of purples because the probability of having all 3 of them be purple is fairly high. So we must have had a kind of a biased bag with a bunch of purple jelly beans in it. But what we want to do is find the mean, or over the long term, if I kept scooping my hand into this bag and pulling out 3 jelly beans, how many would I expect to be purple over the long term of multiple experiments? And I'm going to find this by just multiplying the probability times the event number. So the event number is the x, and the probability is given. We're going to multiply straight across. 1 times 0.25 is 0.25. 2 times 0.1 is 0.2. And 3 times 0.45 is 1.35. We'll go ahead and then add these together. And I have 1.8. Over the long term, if I kept reaching my hand into those jelly bean bags, pulling out 3, I'd expect to have, just about 2 purple jelly beans in my little group. So that's the mean, or the expected value. We can also find the standard deviation, which is a measure of how spread out the data is. And the steps are given in terms of what we want to do, but I think it's interesting to look at the steps in terms of an example and see this occurring. We're going to multiply the event squared times the probability. So let's take a look at our table. The first thing I'm going to do is create a little column in between here, which is x squared, or the x value times itself. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. And 3 times 3 is 9. This is the event squared, or x squared. I'm going to then multiply these by my probabilities. 0 times anything is 0. That's an easy one. 1 times anything is itself. 4 times 0.1 is 0.4. And 9 times 0.45 is 4.05. Let's go back and look at my steps for a moment. Multiply x squared, or the event squared, times the probability. Did that. Add them together. So I'm going to go ahead. I do recommend definite use of a calculator for this. I'm going to add these values together. 4.05 plus 0.4 plus 0.25 is 4.7. Let's go cross that off my list. Subtract the mean squared. Well, before I could subtract the mean squared, I have to remember the mean was 1.8. So the mean was 1.8. The mean squared then is 1.8 squared, or 3.24. So I'm going to subtract 3.24 from this value. 4.7 minus 3.24 is 1.46. This is our variance. Okay. Now I want to find the standard deviation. This is our variance. Check. We have the variance. I want to find the standard deviation, and I'm going to do this. Represented. Standard deviation is represented with a funny looking symbol. I call it a tipped over 9. It looks almost like a 9 on its side. I should put the little x's with these means because they should be the mean of the distribution x. And we want to take the square root of the variance. So I want to take whatever I got when I subtracted the mean squared and take the square root of it. Now you're thinking, how the heck do I take the square root of something? You have your Windows calculator, correct? Here it is. You can have this in either view. Mine happens to be in a scientific view. It really doesn't matter. But I just want to put my value in, 1.46, and you'll see a check mark here over in the very right-hand column up towards the top. That's your square root symbol. I hit the button, and it's square root of 1.46. It looks like about 1.21. And this is my standard deviation. So you've successfully calculated the mean and the standard deviation of a discrete probability distribution.